Okay, so we're starting with the topic on higher order differential equations. You've already done differential equations in the first semester, which was first order differential equations. Now you have higher order differential equations. So what do you see in higher order differential equations? You basically see the derivative terms. And if you look at the derivative terms over here and out here, they're all higher order. Like in this case, this is a higher order derivative with derivative equal to the order of the derivative equal to n. And if you notice, you also have constant coefficients attached to these derivative terms. For instance, you have an, you have an minus 1, you have an minus 2, an minus 3, a naught, an. All these are constant coefficients attached to the derivative terms. So what exactly are you expecting to see in a higher order differential equation? On the right hand side, you will see that you have a term qx. What is q of x? Q of x is basically nothing but a function of x. So you have a function of x out here. It could be any function. It could be a linear function. It could be an exponential function, a trigonometric function. It could basically be anything. So moving on. Now what is important is these derivative terms or the differentials d by dx, I can basically write it as an operator d. Now what is this operator d? Operator D is just another notation that you would be using for the differential operator. So whenever I have d by dx, I can replace that by capital D. So that's what we can do in equation 1. So in equation 1, what I've done is d by dx that you have here, I can write it as a n capital D raised to n plus a n minus 1 capital D raised to n minus 1 plus dot 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 all of this plus a1 capital D plus a naught, all of this will be operated on y. So I'm just replacing d by dx with the operator d. Moving on, you will see that's what has happened. Capital D operated on y is simply dy by dx. D square operated on y is simply d square y by dxy, which is nothing but the second derivative of y with respect to x. Capital D raised to n operated on y is simply the nth derivative of y with respect to x. So this is what we can basically go on to, and this is exactly what I had mentioned. You can write equation 1 in terms of this equation. Now what have I done? I've basically written equation 1 back again like this, and I have set the right hand side as equal to 0. So if you look at equation 1, if you go back to equation 1 has a q of x on the right hand side, whereas on this side, for this particular differential equation, I have got a 0 on this side. So this equation, I've called it as equation 2, and it is going to be called as the homogeneous differential equation. What is a homogeneous differential equation? It is basically just setting the right hand side of equation 1 to 0. Now what we need to do is we basically need to find out the complete solution of equation 1. Now what is a complete solution of equation 1? It is the complementary function plus the particular integral. So our question would be, how do we find the complementary function plus the particular integral? So that's what we're going on to. So the complete solution is complementary function plus particular integral, which is given by yc plus yp. The first question we will ask ourselves is, let us go ahead to find yc. How do I find yc? Yc is the complementary function, and I will find yc from the homogeneous part of the differential equation. That means I'm setting d raised to n an plus d raised to an minus 1 d raised to n minus 1 plus dot 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 all operated on y. I'm setting it as equal to 0. I'm going to consider this equation, which is my equation 2. So equation 2 is basically what I'm going to be dealing with in order to get the complementary function. So how do I get the complementary function? Once I consider the homogeneous differential equation, which is given as follows. This is your homogeneous differential equation. I will go ahead to find what is called as the auxiliary equation. Now, what is the auxiliary equation? Now, this is important. How do I find the auxiliary equation? The auxiliary equation is basically d by dx, which we normally write as capital D. In the auxiliary equation, either d by dx or capital D, I will write it as equal to m. So if you have the nth derivative with respect to x or d raised to n, it will change to m raised to n. So basically, from the homogeneous differential equation, I will write out the auxiliary equation. Now, what is this auxiliary equation? Equation 3 that is put over here, this is basically the auxiliary equation. Now, what we need to do with the auxiliary equation, an minus 1, an minus 2, an minus 3 are all got from the differential equation. So, those are the constant coefficients, and we get all of this basically from the homogeneous differential equation. What we need to do is we need to solve this auxiliary equation and find the roots of m. Once we find the roots of m, we will have to understand the nature of the roots of m. The remaining part will be in the next video.